blades, usually in curvature. For the fans and blowers, they will be straight pipes. For the pumps, that will be in the curved cross section, like this. In case of fans and blowers, they'll be flat line. They'll be flat instead of curved. They'll be just flat. Just flat. So, as I just explained, in case of fan, when this impeller rotates, when the impeller rotates, whatever other clockwise or counterclockwise direction, when the impeller rotates, what will happen at the center point? Always there will be generation or the creation of vacuum pressure. We always, because of the centrifugal force, and centrifugal force acts in the same direction, and once the fluid displaces, and that places the once the initial rotation, the fluid displaced outside, and definitely there will be vacuum generation. The vacuum generation always happens at the center point. So you can see here, I just put a cross section. This is the shaft. When the shaft rotates, then the whole casing rotates. This is the impeller casing. Whole impeller casing rotates, but the vacuum generates at the center. The vacuum generates at the center. This center, this center is connected to well or whatever the tank from where we need to pull the water. We need to pull the water. So here, let's say this is the well, open well, and here we have the atmospheric pressure. Here we have the atmospheric pressure, and here we have the vacuum pressure. So the pressure here it will be lower. Let's say this is the P1 pressure. This is the P1 pressure, and here is the vacuum pressure generated by the impeller rotation, that is P2, and we know that P1 is much greater than P2. P1 is much greater than P2. So we know that whenever there is a continuous whenever there is a continuous pipe, and if there is a pressure gradient, whenever we have a continuous pipeline, continuous path, and if we have a pressure gradient, what will happen? What will happen to the fluid? Any guess?
Fluid will flow from high pressure to low pressure.
Yeah, the fluid flow from high pressure low. Very good, thank you. So the fluid moves from the whatever open well or the storage tank to this one. So the fluid moves and enters into this center point at this point. And since the casing rotates because of the curved blades, the fluid is pushed away. So, the here we have the suction pressure or vacuum pressure. The fluid is sucked, and because of the casing blades in the curved shape, that push in the upward direction, and the fluid goes to the surface. The fluid goes into the above the surface. This way, the centrifugal pump or any pump, the basic principle is this one, but this is the typical cross section or working principle of the centrifugal pump. Students, I hope you understood how the centrifugal pump works. Although it is very simple explanation, but I hope you got some idea. I didn't want to go to force balance and all those explanations because this is not the main forum. But since you all should know, I'm trying to give some good basic explanation. Maybe only aware, but those who are not aware, this may be helpful. Any questions, or you understood? Just repeat. I'll repeat in 3-4 sentences. So when the shaft rotates, the impeller rotates. The impeller is attached with a Impeller is attached with a curved blades. When this impeller rotates, because of this centrifugal force and centripetal force acts in the same magnitude and opposite direction, the vacuum pressure generates at the center. This center position is connected to the well, or from where we need to draw the liquid. So once the impeller rotates, the vacuum pressure generates at the center, and that center is connected to the reservoir of liquid from where we need to pull the liquid. And because of the pressure difference between the 2 points, the fluid will flow from high pressure to the low pressure. So that way, the fluid is uh, drawn from the open well or storage tank to the center position of the impeller. Since it's rotating, and we have, as you can see, there is a open channels. There's open channels for the fluid to flow, and this is rotating. And once the fluid comes here, since this is rotating, the centrifugal force acts on the fluid. The centrifugal force acts on the fluid, mv square by r. And we all know the centrifugal force always acts in the outward direction. Because of that centrifugal force, the fluid is pushed away from the impeller. That way, that way the fluid goes up. That way the fluid goes up. Now, sometimes when you turn on the pump, no water comes. Sometimes you turn on the pump, no water comes. Any so why that phenomena happens? Why that phenomena happens? If the vacuum generated at this position, if is very high, let's say if the vacuum generated is, see the watch, huh? So please wait. So sometimes you take a very low capacity pump. Not this. I will give you in 5 minutes. Wait. So if you take a low capacity pump, let's say if you take the low capacity pump, it can only generate very little amount of vacuum. If the depth of the fluid is very high, and if that vacuum is not sufficient to pull, then water will not come. The water will not come. That is one. Another one is, if you create very high vacuum, and if at that room temperature, if that vacuum is equal to the vapor pressure of the water, what will happen? Whatever water comes, that will become the vapor. And that way also you will not be able to draw the liquid. Both cases, extreme cases, uh, only comes, that is when the distance from the pump to the water level is very high, then only that problems can occur. So yeah, so these are about the centrifugal pump. Students, hope you understood. If you got any questions, please let me know. Yeah. So this is another one of reciprocating pump. This is this is hope I started recording. Let me check. Oh yeah, thank you. Someone has started. So there's another type of pumps that's called positive displacement pumps. They're called reciprocating pumps. What will happen in the reciprocating pumps. Let me give a. So this is a cylinder. This is a simple cylinder. Here we have a shaft, piston. Sorry, here we have a piston. This is the piston. Here we have the piston. The piston moves forward direction. Piston can move in the backward direction. The piston can move in the forward direction and piston can move in the backward direction. How it moves? We all know the cycling, right? We have two wheels, big wheel, and we have a pedal. We have a pedal, and here we have a chain, like black chain. When you rotate this pedal, we all know this chain rotates in the forward and backward direction. One thing goes this way, one chain goes this way, and another chain goes this way. That is the very good example of very good example of secular to linear conversion of secular motion to linear motion. So using that cycle bicycle effect or whatever typical thing, we can connect a rotating shaft in such a way that this moves in up and down, forward and backward, forward and backward direction, forward and backward direction. I hope you all know that very simple one. So here we have, I'll just put blue line. So we have, this is the piston. The blue one is piston. Now, let's say this um, piston cylinder arrangement is connected to a pipe. This piston cylinder arrangement is connected to a pipe. So this is inlet pipe. Inlet pipe, and here we have an outlet pipe. Here we have an outlet pipe. In this pipeline, we have a valve. Here we have a valve. This valve is non-written valve. NRV. Non-written valve. Non-written valve means it accepts the fluid to flow only in one direction. So in this case, it accepts fluid flow only in this direction, down to up. It won't allow the fluid to move from top to bottom. It won't allow. That's type of valve called non-written valves. When you might have seen a typical non-written valve when you pump bicycle tube. It will only allow air to pass through one direction. It won't allow air to come out unless you press the pin inside that one. Hope you all understanding. When you pump the bicycle cycle tire or whatever the tube inside, that wall, whatever is there on the cycle rim, it will only allow air to go in one direction. It won't let the air to come outside. But if you wanted to release the air, you have to just press it. that the special mechanism is there. So similar types of non-written valves, NRV. Sorry, my annotations are not so good. NRV. I could have used better computer because of certain issues. I am not able to. Non-written valve. So it allows only fluid to flow in one direction. So there is one non-written valve in this suction line or inlet line. There is one non-written valve in the discharge line. So this also allows fluid flow only from bottom to up. It will also allow the fluid to flow bottom to up. Right? So hope you are understanding, making some whatever I'm giving. So here this is the closed. This is the closed. This is the closed piston cylinder assembly. Can anyone tell me if the piston moves? Let's say the piston is moving from here to here. What will happen? Let's say initially air is present. Initially air is present. Initially air is present. What will happen when, let's say, the piston is moved from here to here? What will happen?
Water will move in.
Water, no. No water inside, only air is there. Air will go away. It's a
So
water,
the
whatever.
pressure will reduce. So the fluid from the pipe will enter into the.
Oh, okay. True. Ultimately, that will happen. Initially, when you push piston, whatever air is there, that will go away, right? So
Yes.
initially, the tank contains only air. When I move the piston from here to here, whatever air is there, that will go away. Then the valve is closed. When I pull back the piston, when I pull back the piston, what will happen? Since whatever air is present in the cylinder gone outside, there is no air inside. There is no air inside this one. When I pull this piston, when I pull this piston back, what will happen? Since there is no air, since there is no air or very little amount of air is present, obviously the pressure will reduce and there will be generation of vacuum. There will be generation of vacuum, right? When I push the piston first in the forward direction, whatever is air is there, that will go away. Then when I pull the piston in the backward direction, since there is no air, whatever air is there is already emptied. When I pull back the piston, then whole space is filled with vacuum. The whole space is filled with vacuum. Since there is a vacuum pressure here, and if I connect a pipeline to a open well where we have the atmospheric pressure is there or higher pressure is there, and since there's a pressure difference, the fluid flows from bottom to up. The fluid flows from the bottom to up. That way, by the movement of piston, that is the reciprocating action of the piston, vacuum generation, the fluid uh, the fluid discharge, both will happen. Just give me 1 second, students. Yeah, what motion? Sorry. So because of this reciprocating action of this piston makes the fluid move. So that's what is called reciprocating pumps. And here we have the double acting reciprocating pumps. So because in this case suction happens once, then discharge happens once. To mitigate that issue, we have the double acting reciprocating pumps. Anna, all of it. Students, you all understood how this reciprocating pump works? Are you able to hear or disconnected?
Yes, sir, we can hear you.
Okay. Right. So that's about reciprocating pumps. Rotary pumps. In the rotary pumps, we have a spur gears or lube type. There are two types. One is gear pump, and the other one is lube pump. So when this gear rotates, when this gears rotates in the direction, the space filled between these teeth, the gear teeth, basically pushes the liquid. Basically pushes the liquid. Initially, when the gear rotates, whatever fluid present in this casing displaced outside, then this whole area filled with vacuum. Since there is a vacuum generation at the center point and it's connected to the suction line, and because the pressure drop, the fluid flows and the rotation of gear basically pushes the liquid. Same as lube pump. Diaphragm pump. The diaphragm pump. Um, so the diaphragm pump is works using a plastic diaphragm. This is a plastic diaphragm. So what will happen? What will happen? This diaphragm. This is a flexible diaphragm, like a balloon. Right? When you push this diaphragm, when you push the diaphragm, okay. So what will happen when you push the diaphragm? What will happen? Whatever fluid, whatever fluid present in this zone will be pushed this side, pushed this side, right? We just pushing the whole like a bubble. When you push this whole this diaphragm, a plastic, a soft rubbery material. What will happen when you push this down? Whatever fluid is present, that will be go away. Now, when I pull it up, when I pull it up, when I pull it up, it will create some suction. It will create some suction. So, because of the suction line, the fluid comes into this ratio. So, that way, when you lift this up, when you lift the diaphragm or the soft rubbery material, the suction will happen. The fluid comes inside. When you push the soft rubbery material down, that will be pushed to outside. That will be pushed to outside. So that is what here. When you push the diaphragm, when you push the diaphragm this direction, whatever fluid is present in this region, whatever fluid present in this region, that goes outside, goes to discharge line. When I pull this diaphragm, since that will create a suction, the fluid enters into the pump. The fluid enters into the pump. Now, if you see all other pumps has rotating moving parts. All other pumps has the moving parts, whether it takes centrifugal pump, moving metal parts. In case of rotating pump, we have moving metal part. In case of gear pump, we have moving metal parts. But only in the diaphragm pump, there is no moving metal parts. That means when the fluid flows, especially with particles, when the fluid flows, especially when there is a particles, whenever there is a particles flow over a metal surface, moving metal surface, there is a abrasion. The rubbing of particles on the surface of metal takes place. Because of that, the material gets eroded. But in case of diaphragm pump, this is a soft rubbery material. There is no possibility of such abrasion, or very minimal abrasion takes place. The diaphragm is especially used when we have the slurries, whenever the liquid is filled with particles. The diaphragm pump is used, because this is a plastic rubbery material, which is the moving material, and the particle doesn't cause any rubbing or abrasion effect on the surface. The slurries especially used, to transport the slurries, especially the diaphragm pump is used. Guys, we hope you understood why the diaphragm pump is used for the transporting slurries. Okay. So the next type is fans and blowers and compressors. Fans and blowers are similar to the centrifugal pump. Compressors similar to the reciprocating pump. The fans and blowers are similar to the reciprocating pump, and compressors similar to the fans and blowers similar to the centrifugal pumps. Compressors are similar to the reciprocating pumps. So next one is vacuum jet ejectors. Vacuum jet ejectors. We can just now explain that whenever impeller rotates, the vacuum generates at the center. Whenever the piston cylinder arrangement, whenever the piston rotates, again you have the vacuum generates for the fluid to flow. But the amount of vacuum generates there will be quite less. The vacuum generates at that point will be very little. Now, if you want to generate very high vacuum, especially when you want to do the vacuum distillation, or you want to do the any operation at the low pressures, best example is vacuum distillation in the crude distillation unit. In the crude distillation unit, we have the vacuum distillation unit. The whole distillation column is connected to a vacuum generator. The whole distillation column is connected to a, let's say if you want to do the distillation, let's say this is the distillation column, and you want to do whole distillation under vacuum. What to do? This top of this the top of the distillation column is connected to this vacuum generator. The top of the distillation column is connected to this vacuum generator. That way whole vacuum is maintained. You want to do reaction in a low pressure. If you want to do reaction in a low pressure, let's say this is the CSTR. And you want to do at the vacuum pressure. So what we have to do? We have to connect the CSTR. To this vacuum generator. We have to connect the CSTR to this vacuum generator. So that is where whenever you want to generate very high vacuum, like very high vacuum, like almost like 10 millimeters of mercury or 20 millimeters of mercury, there we need very high amount of vacuum. So at that time, we use this vacuum generators called jet ejectors. The vacuum generators are called jet ejectors. Have you heard about jet ejectors? If you already know, I can skip this one. I can assume that you all know it, or
No, sir.
okay. So let me explain. Probably you all know venturi meter. So we have a venturi meter. We have a diverge section. Then we have a converge section. This is the ventimeter. Bernoulli equation says pressure energy, kinetic energy for a fluid which is flowing, of course, the pressure energy delta P by rho plus kinetic energy mv is half v square plus gh equal to constant. Bernoulli equation. The pressure energy plus kinetic energy plus potential energy is constant. If you reduce one, let's say if I increase one, if it is a horizontal, let's say this is a horizontal pipe, so we can neglect potential energy or potential term. So we'll have only pressure term, we have only kinetic term. That is v square by 2. And this one is delta P. This is delta P. So if I increase this, definitely if I increase velocity, obviously I'm decreasing the pressure. That's what the Bernoulli principle uh, indicates us. So in the venturimeter, we have the sudden reduction in the area. When you reduce the area, velocity increases. When you increase the velocity, what will happen? The pressure at this point will be lower than pressure at this point. Then only fluid flows. The pressure at this point, the P1, let's say pressure at this point will definitely higher than the pressure at this point, P2. Pressure at this point, P2. That's we know it. Now let's say I will take a small example. Let's say I'm having a T joint. This is the pipe which is in T shape. I have a pipe in a T shape. If I send water, I have a T shape pipe. Let's say velocity of the fluid is very low. Velocity of the fluid is very low. Can anyone tell me what will happen, how the fluid flows? Will the water come to the, let's say this is point 1, position 1, position 2, position 3. Water goes from position 1 to 3 or 1 to 2. If the velocity of the fluid is very, very low, the water moves from position 1 to 3 or position 1 to 2. Any guess from the students? Here I'm giving, I have a, sorry,
1 to 3.
1 to 3, yes. So this is the T pipe, is a T joint. The fluid is flowing from, fluid is entering at position 1. When the velocity is very low, the water simply goes from 1 to 3. If velocity is high, you listen, hold listen. Velocity is high. What will happen to the fluid movement? Position 1 to 3 or 1 to 2?
1 to 2.
So the fluid moves from 1 to 2. It doesn't go to 1 to 3. The kinetic energy of the fluid is so high, it doesn't want to go other direction. It will go only from 1 to 2. So, but we know that every point there will be pressure and there will be velocity. At every point, there will be pressure and there will be velocity. So what will happen to the pressure at this point? Since the fluid doesn't want to go in the, since the fluid doesn't want to go to point 3, position 3, the fluid want to go only from point 1 to point 2. What will happen? What will happen to pressure at this point? Let's say this is the point. Let's say this is 4. What will happen to pressure at this point? The pressure will start reducing as the fluid moves. The pressure will start reducing, right? Just same effect. Let's say a bus. We are standing. Let's say this is a road, and the bus is moving very fast. The bus is moving. The bus is moving very fast. What do you? Let's say you are standing road and the bus is moving fast. What do you observe? Air is pulled, right? Air is pulled towards the bus. Whatever dust particles and air is pulled towards the bus. Because when an object moves in a very fast, when an object moves in one direction in this case, water moves in this direction, position 1 to 2. Since there is opening here and fluid doesn't want to enter, since the opening here and fluid doesn't want to enter, what will happen here? Here, the pressure, because of the low pressure, it creates the vacuum. It creates the vacuum. It creates the vacuum. When the fluid move at a high velocity, when the fluid move from point 1 to point 2, the fluid will move from point 1 to point 2, doesn't go to the point 3, and because of this high velocity, pressure starts reducing as the fluid flows, and at this point you will observe the vacuum generation. So the same principle is used in the jet ejectors. Here we have to generate very high vacuum, we have to use steam. So the steam is I think the steam is introduced in this line. Here we have the diverging section where the area is reduced. Due to the reduction of area, the fluid velocity will be very high. And this area is open. Since this is open, and very high amount of vacuum generated. At this point. And this whatever open area where vacuum is generated, that is connected to the process vessel. Now, since this is a continuous line from here to here, the pressure profile is applies. So the vacuum is also applied into the pressure vessel. So this is a way by sending a fluid at very high velocities, by creating opening at any intermediate position, we can create the vacuum pressure, and that is the way the vacuum generator works. And this special type of vacuum generator is called jet ejectors. Why we call jet ejectors? The fluid sent into this sent here in like a jet stream, like very high velocity. Sorry, I don't have a proper way to write because I'm not going to the office. I'm not using the department computer. I'm not able to draw properly. I'm very sorry for that, but I hope you're able to understand what I'm explaining. Sorry for the inconvenience. So this is the way vacuum jet or vacuum generator jet ejectors works. This is control valve. I think your process control course is happening now, I guess. This is the control valve. Control valve primarily used to send the fluid at regulated flow rates. The control valve is used fluid to send at the regulated flow rates, either to increase or decrease, or to send at the regulated flow rates. They use control valves. And I think with my bad annotations, it's not a good thing to explain. I'll make an attempt. So here we have the this one. This is the wall. This is the main wall. They call, you can see a triangular shape one. This called wall seat. This called wall seat. You can see this is the valve stem. This valve seat is connected to a valve stem. This is the valve stem. Almost up to this point. Okay. If you apply pressure, here, if you apply pressure on this one, what will happen? The spring moves downwards. The spring moves downwards. When the spring moves downwards, what will happen? The valve seat will move downwards. The valve seat move downwards. If you want to close it, if you want to close the valve, right, you can give enough pressure so that it can completely come and sit here. If you give enough pressure so that they come and sit here, then the valve is closed. The valve is closed. If you wanted to fluid to flow, you can release the pressure, then valve will move upward and the fluid enters. So this way, I'm just giving very blunt explanation, just to understand, because anyway you will learn much more details in process control course. So this way, by using pressure, pneumatic pressure, we can control the valve. We can switch on, we can switch off, or we can regulate the flow rate. So control valve, that is to regulate the flow rate with help of external stimuli. You manually don't need to go and control it. You just have to give a pressure, air pressure, and release the pressure. Automatically, the control valve works without direct manual interference. This is about storage. I don't need to talk about this. Storage tanks. We have three types of storage tanks. One is cylindrical and spherical. Two types cylindrical and spherical. For liquids, we have a flat roof. For gases, we have a hemispherical or toruspherical heads. Then we have silos, bins, and hoopers. Another type of unit operation is cooling towers. You might be learning this in mass transfer course. We cannot introduce hot water. We cannot discharge hot water into the reverse. Like whatever processed water at the end of the usage, we need to introduce into the reverse. We need to send to the reverse or whatever. Now, if it is hard condition, we cannot introduce, because that hard condition can decrease the or increase the BOD level, or can kill the aquatic culture, can create other environmental hazards. So we need to cool the hot water. If you want to cool the hot processed water with help of air, we use cooling towers. So this is natural draft cooling towers, and these are called forced draft cooling towers. Too much theory. I again said this course is a theoretical course. I hope you have to adjust with me. Probably might feel sleepy or whatever, especially in the morning time. This is a bad slot for this course, but I have no choice. So kindly take a sip of water time to time so that you will not get distracted. So we have so far we have seen unit operations. Another important part of chemical process industries is reactors, unit processes, where chemical conversion of one component to other component takes place. So we have two types of reactors: catalytic reactors and non-catalytic reactors. Non-catalytic reactors are very simple. That is plug flow reactors and CSTR, continuously stirred tank reactors. So non-catalytic reactors are used especially if the reactants are fluids. Non-catalytic reactors are used especially if the reactants and products are fluids. But if there is a requirement of catalyst, especially solid catalyst, if we need to use for the reaction, but often we need to use catalyst uh, to enhance the process conditions. We need to use the catalytic reactors. Whenever we use the catalytic reactors, we have a liquid reactants, and we have to also have solid catalyst. So often there will be a one solid catalyst, and often we will have a liquid or gaseous reactants. At that time we use catalytic reactors. If catalyst particles are packed, if the catalyst particles are packed, that is called a packed bed reactor. If the catalyst particles are moving, if the catalyst particles moving along with the reactants or fluids, that is fluidized bed reactor. I have also shown you in the last semester fluidized bed, fluidized bed. So similar to that one is fluidized bed reactor. If particles are very small, if the catalyst particles are very small and they are suspended in the fluid, that is called slurry reactor. That is called slurry reactor. I don't know whether you're all getting whatever I'm trying to say. So, so this is a cylindrical pipe. Here we have a support plate. We have a support plate, and here we have a catalyst particle. These are the catalyst particle. Catalyst particle. If you pack all the catalyst particle like this, if you pack all the catalyst particle like this is called packed bed reactor. Why? The catalyst particles are packed. It is resembles like a packed bed, and when the reactants enters, the reactants is flow over the catalyst particle. When the reactants enters into the reactor, the reactants flow over the particles, and we know that reaction takes place at the catalyst surface. We know that the catalyst reaction takes place at the catalyst surface when you maintain required pressure and temperature conditions. So such type of reactors are called packed bed reactors. Instead of catalyst is packed, instead of catalyst is packed, if the catalysts attempt to move, this is the support plate. The catalysts attempt to move, the catalyst particles attempt to move along with the fluid. So this is the reactant. Reactant flows like this. But catalyst in the packed bed reactor, catalyst particles are stationary. In case of fluidized bed, when the fluidized bed reactor, the catalyst particles moves in the fluid zone. the particles shows like a fluid-like behavior. Such type of reactors called fluid bed reactors. Sometimes we have a CSTR type of reactor. We have CSTR type of reactor, and reactants are liquid. Reactants are liquid. Reactants are liquid. If the particles are very very small, the particles are very very small. Catalyst particles are very very small. Catalyst particles are very very small. Whatever red dots you can see. When particles are very small, more amount of catalyst particles we can put it inside, and this almost looks like a liquid filled with particles, like a slurry, and such type of reactors called slurry reactors. Such type of particles are slurry reactors. So when do we use packed bed reactor? When do we use slurry reactor? If the catalyst particle is not a porous material, if the catalyst particle is not a porous material, we need very very high surface area. If catalyst particles are not porous, we need very very high surface area for a quick reaction or faster reaction to take place. High surface area comes only when we have the very very small particle size. High surface area comes only when we have the very very small particle size. At that time we have to use slurry reactor. If catalyst is highly porous, we can have very very high surface area even if we have bigger particles. If the catalyst is highly porous, if the catalyst is highly porous, we can have very very high surface area even if the particle size is very big, because the pore, it is a porous. All the pore volume is included in the surface area of the particle. So if you have a porous catalyst particle, we will go for packed bed reactor and fluid bed reactor. We have the non-porous catalyst particle. We have to use very fine particles. Then we have to use the slurry reactor. When do we use trickle bed reactor? If the reactant's velocity is very low, if the reactant's velocity needs to be very low, we have to use trickle bed reactor. And trickle bed reactor is preferable if we have two reactants, one is liquid, one is gas. One is liquid, one is gas. Then we go for trickle bed reactor. If one reactant is liquid, another reactant is gas, we need to maintain low velocities at that time. Then we go for the trickle bed reactor. Trickle bed reactor, packed bed reactor looks same. Trickle bed reactor, packed bed reactor reacts same. Only difference is in the trickle bed reactor, the flow like a trickling. Trickling means very very low flow rates. So the total dynamics will change. So that they will discuss in CRE. I don't want to discuss what the dynamics change and all, but I'm giving a quick view. What are the differences? What are the similarities? The packed bed and trickle bed reactor look similar in terms of the construction wise. The only difference is the velocities are low, and trickle bed reactor is preferred to use when we have one reactant liquid and another reactant is gas. If both are gas, let's say all reactants are gases, our products are gases, then we prefer to use packed bed reactor. That is our primary choice. So we will take 5 minutes break. So right now 9:11, we'll start again at 9:15 on these flow diagrams, how to construct a flow diagram or what is the difference between the different flow diagrams. Okay guys, just take 4 minutes break and I will start again. Yeah. Students, do you all understand? Do you have any questions so far? Whatever explained. Do you got any questions? Anyone? Please let me know. Are you able to understand? Making some sense, whatever I'm explaining. No idea. Okay, are you able to hear me? I'm just wondering.
Yes.
Okay, so if it is clear, that is good. So we'll move on. So we have flow diagrams. Flow diagrams, three types of flow diagrams is available. Block diagram, process flow diagram, and piping and instrument diagram. Just like we use Google Map to know how to go from one point to another point, to understand how to go from one point to another point. In chemical industries, we use flow diagrams to understand the overall process. Just like we use a map to understand how to go from one point to another point, in chemical process industries, we use flow diagrams to understand the overall process. Because always pictorial representation helps to understand things very easy. Always pictorial representation helps to understand things very easy. So we use three types of diagrams: block diagram, process flow diagram, and piping and instrumentation diagram, P and ID diagram. So we'll see what are these, what the message they convey. Block diagram. In block diagram, every process, regardless whether it's unit operation or unit process or distillation or extraction, everything is represented in a simple rectangular blocks. Everything is represented as a simple rectangular or square blocks. Whether it's a reactor, whether it's a separator, whether it's a dryer, whether it is a pump or everything, anything and everything will be simply represented by a rectangular or square blocks. That's why it's called a block diagram. Like here, I just shown the hydrogenation of toluene, right? So here, toluene and hydrogen are sent as reactor, and here the reactor is shown in a rectangular block. Then after that, we get the benzene and methane. Then we wanted to separate that one, so we have a gas separator. So then we have the separator. We have distillation column to separate benzene and the trace amounts of toluene, and the toluene is recycled. So this will only tell you that this industry or this plant or this process involves a reactor, a separator. That's all. It doesn't tell you any more details. It doesn't tell you any more details like what temperature, what conditions. It won't tell you. Of course, sometimes they may write, they may not write, but it won't tell you more details about the industrial process. Process flow diagram. The process flow diagram. In the process flow diagram, each process, each process represents with a specific symbol. Like reactor, you will have one symbol. A distillation column, we have another type of symbol. For pump, we will have a specific symbol. For cooler, we have a specific symbol. For a control valve, we have a specific symbol. Like we have a pump here. So we have pump here. It shows with this type of symbol. And we have a heat exchanger. It shows with a specific symbol. This is the heater, we have specific symbol. We have fixed bed reactor, we have specific symbol. And they will also mention what temperature, what pressure in which this fluid is going in, and what temperature at what pressure is coming out from this process. Sometimes they write, they may not write. Then we have a cooler specific symbol for a control valve specific symbol. Then we have this. This is a stripper. We have a specific symbol. So like this, compressor. This is the compressor. We have specific symbol. So each process with more details, more smaller processes also will be explained. Smaller process will be explained, and sometimes they will give the conditions. Sometimes, but broad process conditions they will give. And if it is catalyst bed, they will highlight as a catalyst bed. So as soon as you see this, you will know, you can distinguish. You don't have to read out. In case of block diagram, you have to read out. Okay, this is reactor, this separator. We have to read. Unless you read, you cannot know it. But here, we don't need. We can see by symbols. We can tell. Okay, this is process one. From here, the stream is going to this. So that way, more details, more quicker way of understanding will be understood by a reader. Now, in this course, in the CPT course, we will use process flow diagrams of various industries to understand the overall processes, overall industrial processes. We use this process flow diagrams to understand the overall processes. Now, instead of just putting a process flow diagram and make you explain and just explain, I will want to explain how each and everything comes, starting from the feed, why we use pump, from the pump, why we use heat exchanger, then what heat exchanger, why are we using this reactor, what is the need for the reactor. Like that, I wanted to explain one by one so that you don't have to by heart any process flow diagram. You can simply, if you understand some of the basic details, you will be able to construct your own process flow diagram. In the normal regular courses, you need to draw this process flow diagram as part of exam. But in this online exams, we will not ask you to draw these process flow diagrams. Rather, we will ask small questions on these process flows. Why we use heat exchanger, or what is the need for the fixed bed reactor? What is the need for the control valve at this point? So those kind of, the whole big process flow diagram will be reduced into small questions and will be given to you as part of the exam. Now, further, now for an outsiders, like an outside person, this block diagram and process flow diagram is only available. Like if you visit an industry, often they show only block diagram. Often they show only block diagram. If you insist, if you say I'm expert, I'm a process engineer, I want to understand better, they might show a process flow diagram, but they will never show you P and ID diagram. They will never give you P and ID diagram outside, because P and ID provides more details than the process flow diagram. And in the P and ID diagram, further unique identification of the codes. For example, if you see here, for packet bed absorber, for a extraction column, for absorption column, you will look similar symbol. We will use similar symbols, which I will show you later. What are the symbols for each process? We will use similar symbols. But in the P&D diagram, everything is unique. Unique identification codes, unique symbols will be used so that no repetition between one point to another point. So let me go into more details. What are those unique symbols and how to represent? So let's kindly bear with me. Try to pay attention. So if you have a bold straight line, thick dark line, bold line, that shows the main process. Main process means how the raw materials are sent till to get the products. If any byproduct forms, that won't be represented. That will not be represented by this. Only main products, desired products, will be shown with this bold thick line. So that is the main process. If you see thick black line in the P&ID diagram, that means this is the main process. The desired product is forming in this direction. If you need to use utilities like cooling water, that is utility. Sometime in heat exchanger, we need to use cooling water to cool the fluid, right? So that is where we use utilities, water and air. Water and air as common utilities. So if at all utility line is coming, let's say they're taking a water from somewhere and introducing into this process industry, they will show that utility line with the gray color, very light color line. If we are giving any impulse, either impulse heating or impulse input or impulse anywhere, the instrument impulse, then it will be shown with a dotted red line. The dotted red line. If this pipeline is insulated, if the pipeline is insulated, that will be represented in this way. If the pipe is insulated, because sometimes you are sending a steam from boiler to the reactor. Let's say you are sending steam from a boiler to the reactor. So that pipe, the steam pipe has to be insulated. If you don't insulate, what will happen? The steam will get condensed. The steam will get condensed. So that such type of lines where you pass steam or hot fluid where you don't want to cool it, then we will use the insulated lines. So such type of lines symbols are used to represent the insulated lines. In P and ID, whether it is hot line, insulated line, doesn't matter. We'll just put only simple line. Like let's say when you come out from a heater, they always use the insulated line, but we don't show in the PFD diagram. But in the PFD diagram, we will show that this is insulated. This is the utility line. Like for example, here you need to use cooler. In the cooler, we need to use the cold water, right? So cold water. So at that time, we need to use utility line. So, but we won't show in the PFD diagram whether utility line or some within the process you are connecting or you taking out from the outside utility line. We won't represent. We'll just put it as a cooler only. But in the PND diagram, you will have to show whether it's using utility or within the process you are connecting one stream to another stream. Then trace heated. This is the trace heated simplest line. Trace heated simplest line. So here, what is called trace heating, you have to understand. Let's say this is the pipeline. So this is the pipeline. You are sending a fluid. You are sending a fluid at specific temperature. While the fluid going from here to here, you don't want temperature to reduce. You don't want temperature to reduce. At that time, what we do, we provide some heating. We provide some heating. One way is we can just put a coil. You can just put a coil like coil heater we use for in winter season. If you want, we use coil heaters. Similar to that, we use a coil and it is connected to power supply. It's connected to power supply. So the coil, whenever you apply, whenever you connect a magnet like iron coil or copper coil to the electric power, and it will be the temperature of that will increase, and that way heat transfer takes place from this coil to this inside pipe. That way the fluid temperature can be maintained. So this is when you want to use if you have, when you want, this is along the pipeline. This is along the pipeline. You are putting this coil and you're heating it. You are heating it. So that such thing is called traced heated line. Trace heated line. Okay, tracing along the pipeline. You are providing some sort of mechanism to maintain the temperature. That is called trace heated. if we use simple just coil, very less temperatures, we'll just use simple coil, then we use simplest. Sometimes we need to insulate it, then use further complicated thing, then we call the trace heated line. Now, if you're using if you want to heat some, let's say you have a tank, you have a tank, and you are heating the fluid inside by using electric coil, then we will use electrically heated coil line. Sometimes we have the lagged pipe where we use losing the heat, where we are losing the heat, and that time we will say a lagged pipeline. Now, if you're using electrical impulse, if you're using electric shock or electrical impulse, then we will represent it with a symbol. If we have a jacketed heater, we know double pipe exchanger. We have seen the jacketed heater. At the time, we use the jacketed heating. Then we have the mechanical link between one pipeline and another pipeline. Let's say we have one pipe and screwed with another pipe, screwed with this other pipe. Then we have the joint here, right? We have the mechanical joint between these two pipelines. So there we have to represent this one. If we use impulse with help of the air pressure, then we call it pneumatic impulse. This way, each and everything, each and every details we can understand by using the P&I diagram. If you see the P&I diagram, we'll quickly know whatever all, like the person who fabricates the instrument, that guy knows all these details. But for us to know, we have to open and see everything. But we don't need to do if we have a P&I diagram. Now, each
Sir,
pipeline,
sir,
yes,
sir, could you please explain the lagged line again?
right. So uh, suppose we have a hot iron rod. Okay, hot iron rod. Now, um, to to not to reduce this temperature, what we do, we often we often place some insulating materials. We place some insulating materials. We place some insulating materials. Even after you placing the insulating materials, what will happen? There'll be certain amount of temperature drop will happen. The certain amount of temperature drop will happen. So the place or the condition where the pipeline where or the process conditions where we are seeing that loss of temperature or we have certain amount of insulating materials is covered, still we see certain lagging in the temperature. There we use this type of thing, lagged pipe.
Okay, sir. So then what's the difference between insulated and lagged?
Yeah. So in insulated, we assume that the temperature drop is not significant. Let's say we have inlet temperature, outlet temperature, right? We don't see a big drop, not considerable drop. We could get a perfect, like very good insulation. But in case of lagging, even after insulation, still we will see a drop in temperature. That drop in temperature is still significant.
Okay, sir. Thank you, sir.
Yeah, yeah. Thank you. So probably we do lagged pipe apparatus in heat exchange in heat transfer course, where we see I don't know whether I don't know, I haven't taken heat transfer lab here, but earlier we used to have apparatus called lagged pipe apparatus. We used to have multiple insulating materials and we used to study how this temperature drop is taking place. Have you studied such experiment in your heat transfer course?
No, sir, we haven't done lagged pipe in
Ah,
heat transfer course.
okay. It's actually similar to the insulation only, but only thing is the drop in temperature is significant. Then only we will get this representation. Hope you understood. Hope my answer. Hope you understood, right?
Yes, sir. Yes, sir.
So this is line labeling. Let's say we have a pipeline. We have a pipeline. In P&ID diagram, line labeling will be given. This is called line labeling. So every line label will have four things. First one is what is the size of this pipe? What is the size of this pipe? For what service it is used for? That means what fluid it is flowing. What fluid which is flowing. For what service it is being used for? What is the material of construction? The pipe is made of, the line is made of what type of material? Whether insulation is there or not. When insulation is there or not, that will be represented in a line labels. For example, 4 inch. The four double lines is 4 inch. So the pipeline size is 4 inches. Nitrogen is flowing through this pipeline, and this pipeline is made of carbon steel. CS means carbon steel. SS means stainless steel. No, N means no. No insulation is provided on this one. If a line label shows like this 4-inch NCSN, that is 4-inch pipe, nitrogen is flowing to this one, and this pipe is made of carbon steel, and no insulation is there on this pipeline. Sorry. So, so that is the line labels. In this case, we have 4-inch pipe, nitrogen is flowing through this one, the line is made of stainless steel, and no insulation is provided. In this case, 0.5-inch pipeline, C4 Heston butane is flowing through this pipeline. It's made of carbon steel. No insulation is provided. This way, using line labels, we will get in the process P&I diagram what material, what is this, everything we will be knowing. Now, what is this square blocks 39 and 43? 39, this pipeline is coming from the process 39. This 39 will be represented in the, let's say we can't use everything in one small A4 sheet or one small paper, right? So there will be multiple sheets, multiple charts will be there, because we are putting so much information, it's not possible to put in one chart. So if you are drawing from one chart to another chart, this 39 refers to the process 39 in the previous chart. The 39 refers to the, this pipeline is coming from the process 39 in the previous chart. This 40 refers to the pipeline is coming connected to the process. The pipeline is coming from process 43. Now this is the control valve. So each control valve represented with the number, so that in the connections we can easily understand from which number to which number. And if you ever visit industry, you can see this numbering also in the industries, or in the wall they will put a sticker with V204, sticker with 205. Even the process also named with 39. You can see this line labeling on the pipeline also. You'll be able to see this line labeling on the pipelines also in the process in the industry, and you can see same thing in the P&ID diagram also. So since we are there putting a lot of information in each and every minute detail, P&ID diagram is not open to outsiders. It's only for the people who work in that industry. Apart from control valves, we have many other valves are there. We have many other valves. Probably you know already if you have done other courses, teachers might have taught you. Gate valve, globe valve, ball valve, and butterfly valve. So gate valve is shown with the symbol, globe valve is shown with the symbol, and ball valve is shown. So butterfly valve. Just now I have shown diaphragm pump. Similar to that, we have a diaphragm valve. It's shown with diaphragm valve. This is check valve and swing check valve, and the symbol with needle valve. If you have a three-way valves, if you have a three-way valves, probably you already know how the typical three-way valve works. And this is the three-way valve symbol. And we have the pressure relief valve. Like in a pressure cooker, you might have seen a safety valve. Like if the pressure inside is very high, like we have two things right in pressure cooker. One is one that makes sound. I also don't know exact name for that one. So one makes the sound, and we also have a very like a nut kind of thing, soft one. If some by any chance if that gets stuck, by any chance if gets stuck, what will happen if the pressure builds up very high in this pressure cooker, you will see the safety valve breaks. You will see that the safety valve breaks. So this is the safety valve. So this is the relief valve. So what mean the relief valve in the process? In the process, let's say this valve is connected to a process vessel, and inside the pressure is inside the process vessel, certain amount of pressure is there. If you put a relief valve which says 2 bar gauge pressure, if the pressure inside the process vessel crosses 2 bar gauge pressure, the safety valve breaks. The safety valve breaks, or it does the relief. It releases the gases, whatever is present inside. It releases the gases, whatever is present inside. Hope you understand. Relief valve. If 2 bar G means if the pressure inside this process vessel crosses 2 bar gauge pressure, this valve will be simply open and it releases the gases whatever inside, so that the process vessel will not break. So that the process vessel will not break. So probably you all know incident, LG Polymers incident happens in Visakhapatnam probably 2 years ago. And the storage tank has this relief valve. The storage tank is this relief valve. Unfortunately, they had a very old storage tank. I was actually be part of the team to mitigate that emission, so I know what's happened there. So that's I'm giving little analysis. All I cannot discuss all the detail. So they have the storage tank. They have the storage tank. From this, they have the vapors are coming, and that vapors only cause the whole issue. So ideally, the vapors which is hazardous to the environment or human beings, they should not put this way. Whatever vapors emitted, that should go to another tank and store it. That's what often does in the various industries. If the vapors are very hazardous, the relief valve should connect to some other process vessel where this vapor should go and store. But they don't have this storage tank. So as soon as the pressure increased or the temperature increased, the relief valve opened and all the vapors came up suddenly and form a cloud mist around this Visakhapatnam area and caused a lot of trouble. So that is where this relief valve helpful. Sorry, the relief valve helps to protect from the major damage, especially damage of the process vessel. So these are the valve symbols. Any doubts in the valve symbols? Good, no doubts. Then we have valve actuators. Now, here I shown, when I explain this control valve, I have shown you here this. You can move this when you move the spring down. When you move this spring, when you move the spring down, the valve seat moves down and closes it. When you move the spring, when you apply pressure, when you push it the spring down, the valve seat moves down and closes. Now you can move this. You can move this by various means. You can move this by various means. That is called valve actuators. If you are operating by hand, you can push the spring by hand. Like in home, if you want to close the valve, open the valve, we use hand operated valve. This is the symbol for hand operated valve. Now there are two types of control valves: fail to close, fail to open. Fail to close, fail to open. I will come to this. If you use solenoid based, if you use solenoid, electrically operated valve, solenoid based, then we have S electrically. By using electric power, if you use solenoids to move the spring up and down, this is solenoid based valve. If you use motor operated valve, and if you use pneumatic pressure, if you use pneumatic pressure, pressure reducing, pressure increasing, we have these valves. Now, have you heard about fail to close, fail to open control valve? If not, I think you will get to know in the process control course. Uh, so fail to open, fail to close. Do you know, student? Do you know, or do you want me to give a quick explanation? Fail to close, fail to open.
Sir, explanation.
Okay. So sorry. This is one of the important setting in control valve. Let's say this is the reactor, and exothermic reaction is taking place. When exothermic reaction taking place, what will happen inside the reactor? What will happen to temperature inside the reactor? When exothermic reaction takes place, what will happen to the temperature inside the reactor?
Increase.
Increases. So we need to regulate the temperature, because if we increase to very high temperature, one thing will happen is that the reaction efficiency will reduce. Another thing is that the process vessel may get damaged or accident may happen. So to avoid that rising temperature, we will have a jacketed vessel. The whole reactor is connected with a jacketed vessel. Through this jacketed vessel, what we will do? We will send cooling water. We will send cooling water. We will send cooling water. CW, cooling water. That cooling water circulates around the reactor, so that the temperature inside the reactor will not cross the certain safety level. The temperature inside the reactor will not cross the certain safety level. Now this inlet line, let's say this inlet water line is connected to a control valve. This is connected to a control valve. This control valve is operated by either pneumatically or electrically. This control valve is operated either by pneumatically or by electrically. Let's say Sometimes this pneumatic pressure line is broken, or suddenly power got off. Suddenly power got off. What will happen? Let's say this control valve is being this inlet water is being controlled by a control valve, and the control valve is operated by either using air pressure, or by using a electrical line. Let's say suddenly the power got off. What will happen? What will happen when suddenly when the power got off? When the power got off, what should happen? The wall should close, or wall should open. Let's say suddenly some power failure happened. This is then we have a what to say. Hmm. If I have a better board, I could have explained much nicely. Uh, right. One second. So this is the pipeline. So this is the valve seat, and this is moving up and down. This is valve seat is moving up and down. When valve seat moves up, this is fully open. The fluid goes through this one. If valve seat goes up, this completely open, fluid will go. If valve seat moves completely down, everything is blocked, no fluid will go. Fail to open means if there is any power failure or air pressure line is suddenly broken, by default valve will be fully open. By default, valve will be fully open. So the reason for maintaining that whenever there is a failure in control valve, the valve will be fully open, so that the maximum amount of water will go and reactor will be run in the safety condition. So that is called when you when there's a failure in the pneumatic signal or electrical line to this one, valve will be fully closed if it is failed to close. If it is failed to close means whenever there is a failure in electrical power or pneumatic pressure, the valve will be fully closed. Fail to open means whenever there is a failure in electrical signal or power air pressure, then valve will be fully open. Certain conditions, in this case, we wanted to maintain the temperature in the reactor to be set in safety level. So we wanted maximum flow rate to be happen. So here the fail to open is required. Sometimes we have the fail to close is required. Sometimes we have the fail to close is required. At that time, there will be, I'm not suddenly getting the example. There are very classic example when to use fail to open, fail to close. Both examples definitely will be given in your instrumentation and process control. Suddenly, not remembering those examples. Very popular, I also know it, but suddenly not remembering. So sometimes the valve we need to close by default by open. At that time, we will use fail to close and fail to open. Transmitters. If we were to measure the flow rate, we use orifice meter, turbine meter, some other undefined meter. These are the symbols to represent these flow transmitters. Now we have many lines. If the pipeline is used for analysis, we will use A. If conductivity is C, if you are using the density or voltage, these are the identification letters used in the P&ID. So these are a typical P&ID diagram of a bubble column. So the bubble column has a pressure relief valve, bubble column has a control valve, bubble column has a jacketed vessel, and the whatever fluid going inside the bubble column is going to process 91, and the control 123 is operated. It has pressure controller, level controller, and temperature controller. TC means temperature controller, LC means level controller, PC means pressure controller. So this TC, the temperature controller, is connected to the control valve 123. This level control is connected to control valve 104, 105, 106, 107. That's what this means. This pressure control signal is going to the control valve 107. So that way, each and every minute details of a process, whole industry is given in this P and ID diagram. I just shown the P and D diagram of a distillation column. So this is this much complicated. I didn't get any clear because these P and IDs are not open for the normal one. So I got only rough picture from a textbook, and it's not clear. But just to show that it has each and every detail, and this is very complicated diagram, and is only available for the people who works in this industry. And from the P and ID we can get all the information. So that's all about P and IDs and all the flow diagrams. I hope I've given you enough details to read P and ID diagram. Probably it will be beneficial if at all you visit any industry or if you go to any internship. Okay, that's all from me for today. If you got any questions, let me know. Students, are you understanding? Are you able to follow P and ID?
Yes, sir.
So, any questions, students? Any questions?